Welcome to the second lecture for our class. I guess before I begin, just one quick kind of reminder slash announcement. So, there's basically no discussion except me just talking to myself on Diderot so far. So I assume that's because everything is crystal clear and everything is super fun. But of course, remember that if you have any questions or you want to begin any discussion, it doesn't have to be a question, or it could be a complaint, or or it could be some comment that you had on something that we did. You could always make a post on Diderot. Um, Usually, your questions would be much more useful to other people too. So in general, it's good to have discussions over there rather than email, for example. Okay, very good. So let's begin. So today, what we're going to do, so we kind of saw some basic definitional aspects and some duality of pseudo distributions and some of squares proofs the last time. This time, we are going to look at some algorithmic aspects and look at the first application uh, of the sum of squares algorithm by basically recasting this famous result of Gormans and Williamson into this, sum of squares language and basically, reproving it in this world. So that's our plan. So yeah, let's begin. So recall, we had we were looking at functions on the hypercube, right? And we discussed why we can always somehow think of these functions as multilinear without loss of generality, because that's how things are on the hypercube. And let's say it's a degree d polynomial. So last time we discussed sum of square certificates of non-negativity of f. So let's say suppose f does indeed have a degree d certificate of non-negativity. What that means, if you remember correctly, is that f actually equals a sum of some polynomials gi. Each gi has degree at most d over 2, and this equality holds over the hypercube, meaning that they're equal as functions on all possible points in the n-dimensional hypercube. The question we are interested in today is, suppose such a representation exists, how can we find it, right? So how can we compute it? And we also did this duality theorem where we said, well, if f does not have a degree d certificate of this form, then we know in fact that there exists a dual object, the pseudo distribution, right? So suppose f does not have such a certificate, well, then we know that there exists a pseudo distribution such that the pseudo expectation with respect to the pseudo distribution mu f is strictly negative. And so same question, right? Can we find such a pseudo distribution? And so we're going to look at algorithms for computing both these objects, and that will be the first part of the lecture, and then we'll apply it to solving MaxCut today. So let's examine the first question. So for the first question, last time we proved, so if f, so we are assuming that f is given to us in some form, so we always assume that f has rational coefficients, and the input size is basically the number of bits required to express the two integers representing each coefficient. That's what we discussed. We call this the bit complexity. And so let's say f has rational coefficients of some bit complexity, and is has a degree d sum of squares certificate. Then in fact we proved that in fact you can assume that the number of polynomials appearing in the certificate are small. So we can assume that f actually is some gi square I from 1 through r for r at most n to the d over 2. Okay, that was kind of the first step. We showed why in fact whenever there is a certificate, we can assume that it's actually short certificate in some form. The other claim I made was that we can take the coefficients of gi themselves to be rational numbers, with bit complexity polynomial in the size of the representation of f. And in the first test of whether you were paying attention and how many of were you sleeping, I have to declare that this claim I made was false. So, we are beginning our lecture today with some excitement. This is false. Okay. So hopefully you're all awake now. So let me discuss this because it's very interesting, and I realized this when I was writing down the notes and trying to prove it. And I realized that I have chanced myself upon a great open question, which I'm going to, start by telling you about. So this is false. In fact, this is not clear at all. I don't know if it's false, but it's certainly not known to me whether it is true. So what am I talking about? I'm saying, suppose f has, so, what is this question? So let me write it down. Because, it's the first open question we are discussing in this seminar right now. So let's say, f is a, degree d polynomial. Or actually, suppose f has rational coefficients. And, by clearing the denominator, you can always assume that they are in fact integer coefficients if you like. Let's say, f has a degree d SOS certificate. Then the question we're asking is there always a degree d certificate where the constituent polynomials themselves have rational coefficients? So you understand the question? Feel free to ask me questions about this part, okay? Because I found that I was also a little bit confused when I was trying to write notes about this. So, what we are saying is, f itself has rational coefficients. And, we are promised that f has a representation like this, right? As some sum of squares of degree at most d over 2 polynomials. And the question I guess I'm asking is, can we assume somehow that, these GIs themselves have rational coefficients? And this is not clear at all. And in fact, it could be that in fact such a representation does not exist. Such a representation where GIs also have rational coefficients may not even exist. So in particular, it turns out, it turns out that, in about, I guess, 10 years ago, this question was actually asked by Sturmfels. The question above, except he was not asking in the context of the hypercube. He was asking about, sum of squares, polynomials, representations over the, over all of Rn. And, it was actually answered in 2013 by Scheiderer. Hope I'm getting the name right. And Scheiderer proved that, in fact, such a representation does not exist. So what he proved was that there exists a degree d sum of squares polynomial that does not, with rational coefficients. So the polynomial itself has rational coefficients, but there is no sum of squares certificate, whatever degree, not just degree d. There is no sum of squares certificate representation with rational coefficients. And actually, the polynomial he used is extremely simple, so simple that I can write it down. So I know that looking at this polynomial is not going to give you any insight into why this is true, but I want to express how simple the polynomial is for which this result holds. So it's not like some contrived thingy that you might imagine. It's basically, a degree 4 polynomial in 4 variables. So Scheiderer proves that for this particular polynomial, so he proves that this is a sum of squares polynomial, but that there is actually no sum of squares representation for this polynomial where the constituent polynomials have rational coefficients. So, there is no meaning in talking about bit complexity because, you can't even represent these polynomials with rational coefficients. Okay. But over the hypercube, this is not, as far as I can tell, this is not known. And so, that's your first question, right? Like maybe we can resolve it by the end of this seminar. Good. So we don't know this.
Hey, can I ask a question?
Sure, yes.
Over the hypercube, if you allow for some slack that you only want to show that there's a certificate with bounded bit complexity that is larger than some really tiny negative number, is that known?
We're going to discuss that, but I'm talking about the exact question right now.
Okay.
Good. So, this was about whether SOS certificates exist.
There's a question, another question from
Yeah,
Alex.
go on.
He says, "How does this differ from the lemma that was sketched last week?"
Oh, very good. Yes,
that's lemma he's talking about.
Excellent. Yes, that's exactly what I'm getting to. So last time we kind of did a proof. So clearly there was something going on that we all missed, including me. So what was going on? So remember how we proved it. So what was wrong with our proof? With our proof. Well, the way we began was we said, look, f has rational coefficients, and if it's SOS, then in fact, fx can be represented as quadratic form of some matrix A, right? And then in fact, we went on to prove nice things about A. We proved, for example, that trace of A must in fact actually exactly equal f phi, the empty coefficients of the polynomial f. And then this way we in fact were able to bound the Frobenius norm of A. So we were in fact able to prove that A, the Frobenius norm square, it's at most the trace of A square, which is all equal to f phi square. All this was correct, except all these arguments give that there is a small bit complexity representation of A only if we started with a matrix which was rational to begin with. So in some sense, our proof was correct as long as the matrix A had rational entries, but we never established that the entries of A are rational to begin with. And so that was a step, that I kind of, ate up, and now we know that in fact that step is not so clear that even is possible. So hopefully that explains to you what was going on. So what are we going to do today? We encountered
another question. Emre is asking for intuition about where you got this polynomial f, or rather.
It's an algebraic proof. I don't think I understand how it works. Yeah. Okay. So that's well, that's the story of this issue. In particular, remember that we said that if f has a degree d certificate, then we can actually verify it in polynomial time. Well, this puts like a wrench in that whole effort, right? We just realized that f has a degree d certificate doesn't mean that f has a degree d certificate where the certificates polynomials themselves can be represented efficiently. Okay, so a priori we haven't even established that all degree D certificates are efficiently verifiable. All we have established is that if the degree D certificates happen to be such that the coefficients of the polynomials appearing in them are rational, then in fact our proof shows that they can be assumed to be rational with small bit complexity, and then you can verify them. But we haven't verified that there are rational coefficient polynomial SOS polynomial representations whenever there are degree D certificates to begin with, even over the hypercube. Good. So what are we going to do today? We're going to, resort to some kind of slack, some kind of approximation, in order to make progress. And, this is going to be really powerful. We'll be able to do lots of things with it. But it's kind of good to consider the exact questions before you go on to approximations. So, that was our segue into this exact world, but we'll return back to things that we can do now. So today we will prove. So I'll prove to you that in fact there is a certain approximate sense in which SOS certificates, whenever they exist, in fact short ones, easily verifiable ones, etc., also exist. And the way I'll do it is by not just like proving to you that it exists, but by in fact giving you an algorithm to construct it. So I'll do both those things together now. Okay. So we'll prove is a lemma if f has degree D certificates. Then can find a SOS certificate for f plus epsilon in time polynomial in n to the d and log of 1 over epsilon. Okay, can find, let's say, a degree D certificate. So whenever, you know, whenever f admits a degree D certificate, then in fact, you know, you can find a certificate for f plus epsilon. But think of epsilon as some tiny but fixed positive number. And so, you know, in some sense, you shift f by a tiny positive number. And then we'll show that, you know, for any such f plus epsilon, we can in fact find a certificate in time which is polynomial in n to the d and log of 1 over epsilon. So, you know, for example, just to have a sense of the parameters that are going on here, you know, if you set epsilon equals, let's say, 2 to the minus n, then what we are saying is that, you know, whenever f admits a degree D certificate, we can, in polynomial in n to the d time, we can compute, well, actually, you know, let's say 2 to the n to the d, 2 to the minus n to the d, in fact. Then, you know, we are saying that, you know, in polynomial in n to the d time, we can compute a degree D certificate of non-negativity for f plus 2 to the minus n to the d. Okay, so you can imagine that, you know, this might be enough for several of our purposes, even though, you know, it's not a certificate for f itself. Okay, good. So we'll prove this, and, you know, it will take us into some very interesting SDP solving issues. Let's erase this part. Good. So, you know, and as you see, you know, it's a simple corollary, but, you know, in particular, this implies that whenever f has a degree D certificate, f has a degree D certificate implies that f plus epsilon has a degree D certificate with, you know, r less than or equal to n to the d over 2 polynomials. And size of each of these GIs is at most, you know, polynomial in n to the d and log of 1 over epsilon and size of f. Anyway, I mean, I guess I'm just inferring that there exists such a certificate from the fact that I can actually find it. But, you know, it's a non-trivial thing because we just observed that, you know, this is not clear at all if I make epsilon equals 0. Good. So let's, you know, try to prove it, and then, you know, we'll arrive at a certain nice problem that we'll focus our attention on. So, you know, from the last class, if you remember, f has a degree D certificate. This claim implies that there exists some positive semi-definite matrix A such that fx equals the quadratic form on this monomial tensor. And so, you know, if I have to try to find a certificate for f, I might, you know, as well focus my attention on finding such matrix A, right? So we'll try to find this matrix A instead. Okay, and remember, A is a n plus 1 to the d by n plus 1 to the d matrix. Okay, so it's n to the O of d sized. Good. So let's try to see, you know, how we can find this. So let's try to understand, you know, in some sense, think of it as like a set of constraints on a matrix that we're trying to satisfy so that we can write some mathematical program at the end. So the first constraint is trivial, you know, it's like right in the definition. So we better satisfy that A is positive semi-definite. But there are clearly more constraints that follow from the fact that, you know, this thingy has to hold, this equality has to hold for all x over the hypercube, right? So let's try to understand what this implies, what this means, okay? And so if you remember, so, you know, okay, so let's maybe write it down maybe slowly. So we want to ensure, we want to, you know, phrase some constraints on the entries of A that are equivalent to saying, let's call this polynomial on the right here, by the way, G sub A, okay? Just like every matrix A defines a polynomial. So, you know, what we want is that this polynomial GA of x must agree with fx for every point in the hypercube, right? And so, you know, last time we observed that this is same, this is equivalent to saying that if I do a multilinear reduction on G sub A, so, you know, write down the multilinear polynomial corresponding to G sub A by reducing any monomial to its multilinear version, then, you know, this is equivalent to saying that the multilinear version of GA equals the multilinear version of f. And so now, we can actually, write down a simple equality constraints and follow from this. Let's try to understand what it means. So, the multilinear polynomial representation for G sub A, basically has coefficients for every possible multilinear degree D monomial. And so these two polynomials are equal only if, even only if they're all the coefficients match. So we're going to write one equality constraint for every possible coefficient of G sub A and F, okay? So in particular, it means that for every U, FU, this also, by the way, we wrote the last time, but I'm just recalling. So FU must equal, so FU is the, F hat U is the coefficient of F for monomial U. And remember, U, is some subset of N. It basically corresponds to multilinear monomial. And so F hat U must equal sum over alpha beta. So on the right hand side, I'm trying to index things by the entries of the matrix A. Remember, the entries of the matrix A are indexed by, ordered tuples of ordered D over 2 tuples of indexes of X, right? Because that's how, that's how this tensor works. And so I'm going to write on the right hand side the entry A alpha beta. And now I'm going to collect all possible entries A alpha beta that give me the same monomial. So when does, an entry of A alpha beta give me the monomial U? Well, when I think of A, when I think of alpha and beta as a vector, basically it tells me what is the power of each coordinate. I add alpha and beta, right? That corresponds to multiplying the monomials. And then, I have to do a multilinear reduction that corresponds to just, taking off, taking only the set for which alpha plus beta has an odd entry, right? Because that's what would remain after I do multilinear reduction. Everything else will, cancel out. And so this, let me write it as odd alpha plus beta equals U. So this sum is over all alpha beta, such that the odd entries of the vector alpha plus beta exactly equal the set of coordinates in U, okay? And so it doesn't matter what exactly these is. I guess what I'm trying to convince you of is that it's a linear constraint in the entries of A. And you have one such constraint for all possible, degree D monomials, or, the indexes of the degree D monomials, okay? And so the number of constraints here are n to the n plus 1 to the D. Good. So what have we arrived at? Our task has now become the task of finding a positive semi-definite matrix subject to a bunch of equality constraints. Remember that F hat U is, given to us. We are trying to compute a representation, an SOS representation for F. So the left-hand side here is known to us. We're trying to discover a matrix. And we have basically, discovered that such a matrix must satisfy a bunch of linear equations in its entries, in addition to satisfying positive semi-definiteness. So basically, we have reduced our problem to finding a PSD matrix satisfying some linear equations. Okay, good. So as as my Diderot post might have hinted, this is like a very simple instance of what is called as a semi-definite programming problem. In general, a semi-definite programming, in fact, you can think of this, essentially this is as general as get in some sense. It's basically the problem of finding a PSD matrix subject to some linear equality constraints. And what we have convinced ourselves is that an algorithm for this problem would actually give us an algorithm for computing SOS certificates, okay? So we're going to focus our attention on solving this semi-definite programming problem. So we're going to call it semi-definite programming. And so, the first thing we can ask is, can we, at least find out if given such a system of constraints on a PSD matrix, the first question we should ask is, can we decide feasibility of the system? Okay, remember, that the description, so, F, we have assumed that F has rational coefficients. So this is, perfectly well described system. Okay. It has, finite bit complexity in particular. And so we're asking, given such a expressive system of constraints with the PSDNS constraint thrown in, can we detect feasibility? Does someone want to tell me what the answer to this is? Just to gauge, what our intuitions look like here. Do you think this problem has a efficient algorithm? Feel free to unmute yourself and speak out.
Yes, I think so.
Okay, we have a yes, because that's the answer I was going for. The answer to this is unknown. Believe me. Not known. Okay, this is the SDP feasibility problem. And we actually do not know, if it has a solution, if there is, a polynomial time algorithm for it. But let's revise our goals. Who wants to tell me if we know if this problem is an NP or not? Forget, polynomial time. Is it an NP? Let me not, build too much suspense, but we don't know whether this problem is an NP, in fact. This is in NP. So the best upper bound that we know on this problem, the best that we know in terms of computational complexity, we know that this problem is in P space. And that, uses the so-called existential theory of reals, in which you can just think of, as the problem of detecting if a bunch of real inequalities have a solution. But that's it. Okay, so this is the, so it sounds out, we've reduced our problem to kind of a hard problem, right? By the way, this should not be surprising to you, right? This is kind of related to this issue that we were discussing earlier. When F has a degree D certificate and F has, rational coefficient, does it mean that there is a representation A with rational coefficients? We don't know, right? And you can almost imagine why that would relate to whether, you can efficiently verify solutions, because, it's not even clear that you can write down a solution. So if you can't write down a solution, then, there is not going to be much hope of verifying it. Okay, good. So what are we doing? Well, we're going to approximately solve it. Okay. That's what we can do. Okay. So we are going to look at.
Sorry, I don't understand.
Oops. Okay, so we're going to look at approximate solutions of this. And for that, I get a chance to tell you about this really, really cool theorem of Greshel. Wait, gotta get the spelling right. Greshel, Lowash, and Schreiber from 1981. This is a beautiful, beautiful work that, as I expressed on Diderot, we won't have time to prove because it takes quite a bit of work to prove it. But we're going to, use it, and I'm going to explain to you how it works, at least, in terms of using it. So it's a very general result. It actually, goes beyond semi-definite programming. So here is, what they proved. So let's say, K is a convex set. Let's call it capital N in order to distinguish it from the small n's floating around earlier. So, they defined an object called as a weak separation oracle for K. What's a weak separation oracle? Well, given this set K, a separation oracle for K takes input. So it's an algorithmic primitive. So it takes input, a rational vector. Let's say, X. And some parameter, small parameter epsilon bigger than 0. It either correctly asserts that X is in K plus a small L2 ball. Okay, so basically it says that, if you, I'll draw some diagram to, make sense of this, but, B0 epsilon is the set of all vectors with L2 norm at most epsilon. Okay, so this is an R to the n. So, this is the set of all vectors x such that x2 is at most epsilon. And so, either this primitive correctly asserts that x actually lives in k plus, a tiny ball. So like a tiny enlargement of this set k that you began with, or returns an almost separating hyperplane. Okay, so what does that mean? So in the form of some y not equal to 0 that lives in R to the capital N, such that the inner product of y with this input vector x is bigger, strictly bigger, than y inner product with z minus some tiny slack. This is the L2 norm of the vector y. And this is true for every vector z in k. Okay, so let me explain to you what this is doing by means of a diagram. So, let's say, your k looks like this. It's a very idealized convex set k. So, the enlargement with epsilon ball of k looks like this. And there is some internal thingy that looks like this. And so this oracle takes input some point x. Either it says yes, and in that case it means that x is somewhere here. It may not be inside k, but it's definitely inside this epsilon enlargement of the input k. So this is k. Or it returns a separating hyperplane, but the separating hyperplane doesn't separate x from the body k itself. It separates it from some tiny shell thingy inside it. So the hyperplane kind of looks like this, for example. Okay. So the weak part here is basically this approximation that either so you can somehow test if you are inside an enlargement of k, or you can separate it from some kind of shrinking of k, but you can't exactly do it for k itself. Okay, that's what a weak separation oracle is. So I just want to state the theorem, and then we'll pause and understand this a little bit more. But here is the very cool result that Greshel, Lowas, and Scriber proved in 81. They proved that let k be any convex body. What that means is it's a closed convex bounded set. And let's say, that there are some, let's say, there exist r bigger than small r bigger than 0, such that the ball of radius small r is completely contained inside k. So it has like a non-empty interior. And it is completely contained, actually, this need not be around 0. So let's call it, some point, I don't know, p. So, there is some point p, and a small r length ball around it is completely contained inside the body k, and the body itself is completely contained inside some large ball of radius capital R. Okay, so suppose it is true that b0 small r is contained inside k, and k itself is contained inside b0 big R. Further assume that you have a polytime weak separation oracle for k, then given any rational vector v, we can compute a rational vector x such that x is in the convex body k, and 2, Vx is at least, it's basically an approximate maximizer. So, for all z in k. Okay. The running time of this algorithm is going to be polynomial in log of the ratio of the two radii. log of this approximation parameter and, the dimension. Okay, so let's make sure we understand what's going on. What this is saying is, suppose, you have a convex set which is closed and it's bounded. So in some sense, this B0 capital R is just a quantitative version of the boundedness. Not only is it bounded, we know, let's say, an upper bound on the length of any vector that lies in this capital K. And we are saying, in addition, let's say that you have this algorithm to, either weakly detect if a given point is inside K, or, have like this weak separation, like weak hyperplane, weak separating hyperplane that we just discussed. So let's say you have a weak separation oracle for this set in that form. And it is in some sense, it has like a non-empty interior. So, there's like a full dimensional small ball around some point P that is completely contained inside K. If that holds, then you can approximately maximize any vector V. So you can approximately maximize, V transpose X over X in K. And the approximation is in terms of, this epsilon here. Okay, so you can basically get so you can find a point in the convex body K such that, the inner product of V with X is at least, basically the maximum possible inner product of V with any point in K up to some slack of epsilon. Okay. So we're going to lose approximations when we apply this. Okay, so let's try to apply this to a problem. Remember our problem was, find a PSD matrix that satisfies a bunch of linear equations. Okay. So this is a problem of finding a point inside a certain set. Let's write down that set. Our set looks like A, such that A is PSD. And there are some linear constraints. So let's write it like this. Ci inner product A equals some small bi for, let's say, 1 less I less m. Okay, so a bunch of linear equality constraints. A is positive, semi-definite. So, our goal is find a point inside this. Okay. So is this set convex? So let me answer that. Yes. And just because, the set of PSD matrices is convex, and, the set of points that satisfy a bunch of linear equations is convex, and intersection of convex sets is convex. Okay. So this is convex. That's good. Is it bounded? Well, a priori, it seems like this is not bounded at all, right? A priori, it's not clear why it should be bounded at all, right? Like maybe for whatever reason, there are solutions to this system where, A can take many, arbitrarily large entries. But I claim that, we can add a constraint which bounds the entries of A without really losing anything. So remember, we said that, when we are trying to find this matrix A, we know that, the Frobenius norm of A, which is the sum of the squares of the entries of A, can be assumed to be at most F phi, or I guess F phi square, the constant coefficient of the polynomial F, right? So adding this constraint does not hurt us at all. We know that, if we were feasible before, we are feasible right now. And so it's okay to add this constraint. And with that constraint, we actually have satisfied the boundedness condition too. Okay, very good. So we are convex, we are bounded. It's not very hard to check that this is also closed. And so that, okay, we are doing very good. We seem to be very close to applying this result now, except we haven't checked if there is like a ball contained inside this set. I don't know what to call it. I don't know, let's call it S for now. So I guess we need to somehow verify that there is like a small ball around some point P contained inside S. And actually that is in fact false. And that's because, our set is kind of low dimensional. It satisfies a bunch of equations here. So, if I take any point and, take the ball around it, that's never going to satisfy these equations in general. And so this is actually not true. This set does not contain a small ball. So what are we going to do? Well, we're going to relax. We're going to relax our constraints. So we're going to relax our constraints, and try to find instead a point in this set. So we just basically, introduce an epsilon slack into this. And now, you can show that there is a small ball contained inside this set. This is still convex because, I'm still an intersection of a bunch of inequalities. So we are still, going to satisfy all the constraints above. In addition, I claim that, there is a point around which, a small ball is completely contained inside this set. Why is that going to be this way? So if A satisfies the constraints, as I said, then you can add like a very tiny delta times identity. And the point is that this will still satisfy the constraints because the PSDNS certainly holds. And the delta slack, if you choose delta small enough, I'll still continue to satisfy the equality constraints up to this epsilon slack. And now the point is that, if you perturb with some length delta over 2 ball here, like a very tiny, something that is much tinier than this delta identity, then, we will still continue to satisfy all the constraints and the PSDNS. So we claim that, this P is A plus some tiny delta for some fixed, but tiny delta bigger than 0 works. Okay, so basically, this relaxation of our equality constraints. Yes.
I'm not sure why it is enough to show for delta times the identity, because you want to go to every possible direction.
Yes, exactly. But that's a great question. So the point is that, if I look at A plus delta times identity plus any matrix, let's say, B, and think of B's, Frobenius norm to be much, much smaller than delta, then the point is that A plus delta times identity plus B would always be PSD. Because B's eigenvalues are all smaller than delta, while I have a delta times identity sitting around here. So, this matrix will still be PSD. And in addition, if I control the Frobenius norm of B, I would continue to satisfy all these constraints up to some epsilon slack.
Okay.
Does it make sense? Good. Yeah, that's why this perturbation by delta times identity kind of helps. Good. All right.
Also,
Okay. So we understand that we can approximately solve this. So let's go back to our question now. What have we learned? We've learned that we can somehow relax this equality constraints. We can relax this equality constraints to up to having a slack of plus minus epsilon, and then we can find a PSD matrix subject to these constraints, right? So what does that mean for the question of finding a sum of squares certificate for F? Okay, so now, if we go back, what we actually learn is that, so remember our constraints would look like this, right? So our constraints look like F hat U should equal 1x tensor to the D, F hat U should equal, sum over alpha beta, odd of alpha beta equals U, A alpha beta. And well, we can't satisfy this, but we learned that, we can somehow satisfy it up to some epsilon. So what this means is that can find some F prime such that F prime has a degree D SOS certificate, and Fu minus F prime U is at most epsilon, right? So we can somehow, find some other polynomial. The coefficients of this polynomial are epsilon close to the coefficients of F itself, and F prime will discover a SOS certificate for it because they're going to find a PSD matrix that represents it, right? So we wanted to find an SOS certificate for F. We didn't quite succeed in that. Instead, we were able to find an SOS certificate for some closed polynomial F prime, right? So now what? So, now we know that F of x equals F prime of x plus F minus F prime of x, triviality. And now, we are going to observe that F minus F prime's coefficients are tiny, right? In particular, note, if I sum over all u at most d, the coefficients of f minus f prime, then this is at most epsilon times n to the d, or I guess n plus 1 to the d. Right, because each of the coefficients were close up to epsilon. So the sum of the coefficients is going to be at most some epsilon times some n to the O of d, right? And now remember from our last class, we knew that if we take any polynomial and shift it by the sum of the absolute values of its coefficients, then this polynomial always has a degree d certificate. So what have we learned? Let's call this, number L. Then L plus f minus f prime has a degree d certificate. Good. And so what does that mean? So we know that, f prime has a degree d certificate. F minus f prime plus L has a degree d certificate. It implies that the sum of these has a degree d certificate. In particular, L plus f has a degree d certificate. And L itself was basically epsilon times n plus 1 to the d. So we have proven that epsilon times n plus 1 to the d plus f has a degree d certificate. And in fact, we found it. And so now you see what the game is. We're just gonna make epsilon tiny enough. And we have actually recovered what we wanted to prove by making epsilon tiny enough, epsilon n to the minus d or something much tinier than that. We basically have found what we wanted, like a tiny additive shift of f indeed has a degree d certificate, and not only it has it, we can in fact find it. Okay, so again, 30 seconds pause to take questions. So I'm gonna say this here. Good. So what have we learned? We have learned that whenever there is a degree d certificate, we can in polynomial time find a certificate for f plus epsilon, right? And where the polynomial, has some dependence on log of 1 over epsilon. Very good. So let's look at the second question real quickly. So the second question was, suppose f does not have a degree d certificate. Well, then we know that there is a pseudo distribution such that expectation with respect to it is negative, mu of degree d. And the algorithmic question is, can you find it, right? Can we find such a pseudo distribution? And we are going to basically, do similar, a similar, reduction to semi-definite programming in order to, compute something which is approximately, this object. So what are we going to prove? Let's write it out as a theorem. In this case, there exists a polynomial in n to the d log 1 over epsilon size of f algorithm to compute a pseudo distribution mu such that the pseudo expectation of f is not negative, because that we can't immediately guarantee, but less than epsilon. Okay, so that's the approximate version of this theorem that's the approximate computational version of this thing that we can actually do. Okay, and the proof again is, I'm going to sketch this proof now, but it's kind of simple. Right? Remember, we just make variables for all possible monomials of degree at most d. And then remember, what does it mean? What does it mean for mu to be a pseudo distribution? Well, it means that, the pseudo expectation of 1 is 1. And so, in some sense, we don't even have to make it a variable. We just know that setting is already true. And then, we proved the last time that such an object is a pseudo distribution if this big matrix, the pseudo moment matrix, is positive semi-definite, right? And so the point is, if you look at this matrix, the entries of this are going to be, you know, pseudo expectations of monomials, things like this, right? We have variables for each of those. So this is some PSD-ness constraint over some, you know, matrix where the entries are variables. So this is again going to be a semi-definite programming problem. And I don't want to go into the details, but, you know, a similar kind of discussion that we had yields an algorithm for this problem, you know, which kind of approximately solves it. Oh, and, you know, the negative, so I also have to put this constraint. So we have, you know, basically a semi-definite programming problem with this linear inequality constraint. So, you know, as we learned, we usually cannot satisfy them exactly, but we can satisfy them up to some slack. And so, you know, by introducing this slack epsilon, we end up satisfying this inequality constraint up to epsilon. Okay, so these two kind of algorithms that we just saw, so algorithms for computing SOS certificates or pseudo distributions, they're both, you know, basically primal and dual versions of the so-called SOS algorithm. These two primitives, at least over the hypercube that we studied, we're going to call as the sum of squares algorithm. So at least now you know what the sum of squares algorithm itself is. Good. So actually now again, it's good to take maybe a 30-second pause because we're going to shift to max cut. So again, if there are any questions, we can discuss them. Okay, good. So now, you know, we've learned an algorithm, we're going to apply it to solve, you know, a very basic computational problem. I'm sure, you know, this is a problem that you've seen before. It's the so-called max cut problem. We saw this problem very briefly, you know, in the first lecture. So the input to this problem is a graph, GVE, and we're going to assume that V has n vertices. The goal is to find a subset of vertices so that, you know, the number of edges going outside of this set is maximized. Ij says that one endpoint is in S, the other endpoint is in the complement of S, is maximized. Okay. It's kind of a classical, you know, combinatorial optimization problem. Lots and lots of works have studied this. In particular, max cut is NP hard to compute. So, you know, we are not going to look at, you know, solving this problem exactly. We're not, you know, trying to prove P equals NP today. And I guess, you know, I should remind you that somehow, you know, very tiny, or at least, you know, tiny looking modifications can really change the computational complexity of this problem. So, you know, in particular, you might be aware that the minimization version of this problem, you know, finding a cut where, you know, the number of edges going across it are minimized, in fact, it's easy, you know, has a polynomial time algorithm. So kind of an interesting aside. Okay, good. So, you know, we're going to be interested in approximation algorithms. And this again has a you know, long history. I'm going to give you an algorithm and call it Erdős's algorithm, but, you know, you can see I'm kind of being tongue-in-cheek. Erdős's algorithm. Here it is, Erdős's algorithm. Return a random cut. Can someone tell me what approximation factor this gives? So, you know, in expectation, on an average, this algorithm, you know, cuts half the edges. And this is something that you see probably in the first class on probabilistic method or algorithms or whatever. And so, you know, because the maximum cut can never cut more than all the edges, this is a half approximation algorithm. That's great. So we have our first approximation algorithm for this problem. And, for like, I don't know, for more than half a century, people really thought long and hard on how to improve this basic algorithm of Erdős. It's like, how do you get, a cut which is, larger than, let's say, a random cut, okay? And so, after Kachian's discovery of a polynomial time algorithm for linear programming, there was like a concerted effort in using LPs to solve such problems. So people worked long and hard, in trying to design linear programming based algorithms for max cut. And so, the question was, is there an LP based algorithm? Is there an LP based algorithm that gets a 0.5 plus some fixed constant approximation for max cut? And so, people really tried. People tried adding various inequalities to create, non-trivial LPs, trying to better them. But each time, somehow they discovered that, for various special classes of graphs, you can somehow improve 0.5. But for all graphs, like getting the worst case approximation ratio to improve was somehow not, possible. So they didn't know then, but, we kind of learned formal reasons for this, just a few years ago. So, in a really cool paper, Chan, Lee, Raghavendra, and Steurer. And then, in a work that improved upon this a little bit with Meka and Raghavendra. So we proved, so this is 17, this is 13. So, together these works basically implied that there does not exist a 2 to the n to the delta size LP that gets, 0.5 plus some f of delta approximation. So basically, if you wanted to write a linear program that achieves tiny bit better than 0.5, you will have to, write something that at least has, constraints which are like 2 to the n to the delta for some constant delta. So there is no polynomial size LP. There's actually not even a quasi polynomial size LP for solving this problem. That's great. So what should we do? Well, in 1993, Delorme and Polyak, they came up with like a different approach. And actually they phrased this as certain, certain eigenvalue certificates. We will not discuss their formulation and how they thought about this problem, but they basically gave something that, was different looking than a linear program. And like a couple of years later, people realized that what they're suggesting is like a dual of a certain semi-definite program. And so, we'll just call this what they suggested as an SDP, even though they were talking about certain eigenvalue certificates. So they suggested an SDP to solve this problem. And again, they analyzed it on special classes of graphs, but they didn't succeed in analyzing it for all graphs. And in 1994, the big breakthrough came. So Goemans and Williamson, they managed to analyze the Delorme and Polyak SDP. And they proved that actually it gives you a 0.878 factor approximation for computing the maximum cut. It's like, much, much better than 0.5. And that's what we'll see today. Okay. So let's, phrase it as a theorem. So let G be a graph. And let's call opt G the max cut of G. Okay, so opt of G is basically the number of edges cut by the maximum possible, the best possible cut in graph G. And remember, we call this polynomial FGX. So let's, recall what that was. And so if you recall in the first lecture, basically we showed that this polynomial, is basically a representation of, it actually computes the size of the cut, associated with the set of vertices where X takes, the value 1. So, for X in -1, 1 to the N, maximize this is same as, the max cut problem. Okay. Good. So what are we going to prove? So we're going to prove that there exists a, we're going to prove, so we're going to prove that for all G, so I'm going to phrase it a bit awkwardly, but I'm going to interpret it for you in a second. Opt G over 0.878 minus Fg of X has a degree 2 SOS certificate. Okay, so let's bring it all in one screen. So what are we saying? We're saying that so okay, maybe your first goal was to compute the maximum cut in graph G, but let's say for a second you relax your goal to just finding certificates that bound the size of the maximum cut in the graph G. Okay, so in that case you're trying to prove that FGX is at most some number C. Okay, now what's the best possible certificate you can hope for? Well, clearly, Fg of X can take the value opt of G because there is a cut that, cuts opt of G number of edges. And so the best possible thing that you would want to do here is, prove that opt of G minus Fg of X is always non-negative. That's like saying that Fg of X is, always at most opt of G, right? And so if opt of G minus Fg of X has a degree 2 certificate, then we know that, degree 2 sum of squares, at least up to the slack of epsilon, can, compute this opt of G. Right? And so what we're saying is that we can't quite do that. In fact, we can't expect to do that because this problem is NP hard. We're going to show instead that, if you increase this opt of G number by, 1 over 0.878 factor, then, this relaxation of the max cut upper bound, in fact, does have an SOS certificate. Okay. And in fact, a certificate of just degree 2. Okay, any questions about this? So this is kind of an awkward way to phrase something that you might have seen, but it's kind of nice because we looked at SOS proofs first. So it's kind of nice to look at, what's the certificate version of our theorem. But, I don't want to deprive you, of something that you might be slightly more excited by, even though, we're going to show that they're actually equivalent. We're going to, prove this by giving what is called as a rounding algorithm. So I'll write down the theorem and explain to you what that means. So let mu be a degree 2 pseudo distribution on the hypercube. Then there is an actual distribution, let's call it mu prime, such that expectation mu prime of this cut computing polynomial is at least 0.878 of the pseudo expectation of Fg of X. Okay. So before trying to understand why I'm calling this a rounding algorithm, let's first see that this theorem implies the certificate variant. This theorem implies that I can generate a certificate, of, so actually, in order to talk about this nicely, it's actually nice to interpret this as saying that, I have a certificate that Fgx is at most opt of G over 0.870. And this is just equivalent, right? Like non-negativity, like certificates of non-negativity of opt of G over 0.878 minus F sub G is same as, saying that I have a certificate that Fg of X is at most opt of G over 0.878. Okay. And so let's first see why this rounding theorem here, which I have not explained to you why I'm calling it a rounding theorem, implies that, Fg of X is at most, opt of G over 0.878, or why, this in fact has a degree 2 SOS certificate. Okay. So let's, quickly see proof. Let's maybe call it theorem 2, theorem 1. So proof by theorem 2 implies theorem 1. So how would we argue? We'll say, okay, suppose there is no such certificate. So suppose, and I'm actually doing, simple stuff just so that, this weird way of stating the theorem makes sense. So suppose, this is not SOS. I want to prove that in fact, it has a degree 2 SOS certificate, but let's say it doesn't have it, right? Then, by duality, then there exists a degree 2 pseudo distribution. We proved this the last time, such that, the expectation of this polynomial must be negative. The pseudo expectation of this polynomial must be negative, right? Which is saying, if I just rearrange, that tilde E mu of Fg should be bigger than opt of G over 0.878. Okay. So now, why can't this be true? Why can't this be possible? Well, let's apply theorem 2. Theorem 2 says that, for every pseudo distribution mu, there is some actual distribution mu prime such that expectation with respect to mu prime of Fg is bigger than 0.878 times the pseudo expectation with respect to mu. And now the pseudo expectation we are saying is larger than opt of G over 0.878. So this is strictly, bigger than or equal to 0.870, sorry, wait. Opt of G. And so what have we proven? Well, there has to be a strict inequality somewhere. Here. And so what have we proven? We have proven that under this mu prime, and this cannot happen. Why can't it happen? Well, all cuts in G are of size at most opt of G. So clearly there cannot be any distribution under which the expectation of F sub G is, strictly bigger than opt of G. Okay, so this is a contradiction. Okay. So here we have basically proven that if this theorem 2 is actually true, then in fact, there must be a degree 2 SOS certificate that Fg of X is at most opt of G over 0.878. Again, any questions? Feel free to stop me.
I had a question.
Yes.
Is there a sense in which this formulation of max cut is tight? If you want to improve epsilon over the Gomans-Williamson constant with an SOS2 certificate, do you need some crazy exponential?
We are going to have a very lengthy discussion about what is why this is in what sense it can be tight, in what sense it's not, and so on. So hold on to that question. But we are just beginning with seeing some non-trivial certificate, and it's non-trivial because it improves on 0.5, and then we'll discuss how and if we can improve this. Good. So now I want to maybe before marching on to the proof itself is kind of natural, and many of you might even have seen it before, but I want to explain to you why I look at the theorem 2 here as a rounding algorithm. So, the term rounding kind of comes actually majorly from linear programming based algorithms in the 70s and 80s. So what people used to do in this, and actually still do, is, you take your favorite combinatorial optimization problems, and usually you're looking for, integer, in fact, just 0, 1 solutions to these. So you write what is called as, an integer program. But, integer programming is NP-hard, so usually you cannot solve them. So what you do instead, you relax this integer program to a linear program. And you roughly basically, whatever variables were supposed to take only integer values, in your linear program, they're going to take, so-called fractional values, or they're going to take continuous values. And so in order to somehow, solve your original problem, you take a linear programming solution and somehow, convert it into an integer solution. And, if you're rounding, if you're converting a fractional value into an integer value, you could call it rounding, right? You can kind of rounding off what's going on. And so that's where the terminology comes from. So we're going to stick to the same terminology, but we're going to interpret it kind of more generally. For us, a rounding is simply an operation that takes a pseudo distribution and converts it into a distribution. Okay, that's what our roundings will always mean, taking a pseudo distribution and generating a certain distribution out of it. Okay, so for example, here we have a pseudo distribution over the hypercube, right? And we are trying to find cuts. So we will not try to find cuts directly. We will try to find distributions over cuts. And as you see, our philosophy is that our philosophy is going to be to somehow understand how pseudo distributions are related to actual distributions. So this is not so unnatural. We would like to somehow convert pseudo distributions into a distribution, while somehow being as close as possible in various natural senses to the originating pseudo distribution. Okay, so our roundings will always mean operations that take pseudo distributions to distributions. Okay, very good. So now in this context, you can interpret theorem 2 kind of nicely. You're saying, suppose you have a pseudo distribution mu, and under the pseudo distribution, this cut computing polynomial takes some value. So let's call this in fact opt SOS2. Okay, so it takes some value, right? The pseudo distributions in fact is telling you that, well, I think there is a opt SOS2 sized cut in the graph G. Now we are interested in finding such cuts. In fact, we are trying to understand if there are such cuts, right? So what we'll do is we'll try to somehow find a distribution such that E mu prime FG of X is as large as possible compared to opt SOS2. So we would like to preserve this property that the pseudo expectation of FG is opt SOS2. We would like to preserve this under the actual distribution. We can't quite do that. We'll instead end up only proving that it's at least 0.878 times opt SOS2. Okay, and actually the theorem 2 doesn't say it, but this transformation from mu to mu prime is going to be efficient. So this mu to mu prime is going to be efficient. So in fact, it will give us an algorithm to approximate max cut. Now remember, whenever you go to algorithms, you have to lose the slack. So we will not exactly find this 0.878 opt SOS2. Instead, we'll find a cut where the size of it is 0.878 times opt SOS2 minus epsilon. Okay, good. So hopefully that discussion places what's happening in theorem 2 in some context. Let's now go ahead and prove theorem 2. So, as I said, this is a rounding problem. This is a problem of, taking a pseudo distribution and finding, an actual distribution that somehow behaves similar to it, right? So idealized, the best possible thing that you would have liked to do is, given a pseudo distribution, find an actual distribution such that the first and second moments of mu prime exactly equal that of mu. Right, like before even beginning to understand why we are trying to do approximation, this is the first question we should ask, right? And in fact, this problem is an instance of what is called as a generalized moment problem. So generalized moment problems study the question of when you are given a bunch of numbers that are purported to be the moments of some distribution, some actual distribution, can you find a distribution that, matches those moments? Okay, so here, for example, we were given the moments of the pseudo distribution mu, right? We were given the first moment and the second moment. And you can ask, can I find an actual distribution which has the same first and second moments? So, if over the real numbers, let's say, so actually it turns out that in 1D, even earlier before, even 1D, in one dimension, let's say you were trying to solve this problem, over 1D for distributions over R. It turns out that this problem has a very nice solution. There is a very nice and efficient test of when a given sequence of numbers actually are the moments of a certain actual distribution. And it was solved kind of a century or so ago. And there are various generalizations of this. But as you can imagine, over the hypercube, this problem is not going to be efficiently soluble. And again, like this historical interlude that I did the last time in the first lecture, one of the reasons sum of squares was in fact even developed was to give certain sequence of relaxations for solving the generalized moment problem. Finding distributions with the same moments as a given sequence of numbers. So in particular, Lasserre, he didn't really think of sum of squares proofs when he was developing his relaxations. He was designing this algorithm in order to solve the so-called generalized moment problem. Good. So that's great. We are trying to solve the generalized moment problem, but actually, this is not going to be possible. And one very, very simple reason why it's not going to be possible is because if it were possible, then we would be able to solve max cut exactly. And we know that problem is NP-hard. So certainly, there are computational reasons to expect that this is not going to be easy to do. So instead, we are going to settle for this relaxation, this approximate variant that we wrote earlier. So let's try to see how we're going to do this. And we're going to rely on something you proved on your homework. And it's a very simple observation, which says the following: for any degree 2 pseudo distribution mu, there is an actual distribution over Rn. So we wanted a distribution over plus minus 1 to the n. That's what we would have been very happy with, but we don't know how to do that. Instead, we can actually find an actual distribution over R to the n with same first and second moments. Now the proof is very, very simple. So let me just do it and then we'll take a break. So the first moment of mu is, just the mean here. And the second moment is this. The only observation is that for any pseudo distribution of degree 2, the second moment is going to be positive semi-definite. Okay. And why is this true? Can someone give me like a one-line answer for why this is true? Feel free to unmute yourself.
Ainesh says that all quadratic forms are non-negative.
Yes, but I guess this this is the hazard of the question. It has so many answers which are kind of all equivalent, but I'm looking for the following answer. I'm looking for the answer that we literally had a equivalence which said that mu is a degree 2 pseudo distribution if and only if e mu is 1 and e mu of 1x tensor 2, sorry, actually 1x transposed is PSD. And then observing that this guy is, an n by n principal submatrix of this n plus 1 by n plus 1 matrix, which we know is positive semi-definite. And then we're observing that the principal submatrix of a PSD matrix also has to be PSD. But, I know Ainesh had the same idea, so I'm not looking for this particular answer. But hopefully, you're all convinced that, this PSDNS holds. And I'm going to say that here we are done. And the only observation now is that, for any vector, let's say M, not a great notation, and any PSD matrix, let's call it sigma, there exists a Gaussian distribution with mean M and covariance, covariance sigma. And so I guess this was the second moment, not quite the covariance. So actually, you know, I also want to observe that X minus this guy is also PSD. And again, you know, this follows from the same kind of argument. I guess all we are saying is that, you know, that for any mean, and as long as the covariance matrix of the pseudo distribution is PSD, which it is because that's what a pseudo distribution is, there is a corresponding Gaussian distribution. The Gaussians are not going to take values in plus minus 1. So this is not going to be a distribution, you know, in plus minus 1 to the n. It's a distribution over R to the n, which has the exact same first and second moments. Okay. So, so that's the Gaussian sampling lemma. We're going to, you know, apply this to, you know, complete the proof. But right now we're going to take a 10-minute break before we do that. So, you know, we'll reconvene at 5:41 Eastern time. Okay, thanks so much. So let's resume. So, so remember our goal. Our goal was, you know, to take a pseudo distribution mu and, you know, output some distribution, an actual distribution on the hypercube, right? And our goal was that under the distribution mu prime, the value, you know, of this FG polynomial should be somehow, you know, comparable, let's say within a constant factor, this 0.878 factor of the value of the same polynomial under mu, right? That was our goal. That's what we want to show. Now, you know, using the Gaussian sampling lemma, what we've done is like some kind of an intermediate step. You know, we have basically, you know, converted mu into, let's say, you know, a certain Gaussian random variable G. So far, what's great is that expectation with respect to mu of 1x transpose, meaning, you know, that this encoding of the first and second moments is exactly the same. We've been able to, you know, maintain exactly the same first and second moments, right? So the Gaussian has the same mean and the same covariance. But you know, like the issue is that G does not have plus minus 1 entries. And so our goal is somehow, you know, to somehow take this intermediate Gaussian random variable, which has the same first and second moments as of the pseudo distribution mu, and convert it into some actual distribution over the hypercube. In this process, we are going to lose this property that, you know, we had this first and second moments matching, but, you know, we'll still be able to argue that, you know, we don't lose too much in the max cut value. Okay. So how are we going to do this? And so here is, you know, I'm going to do a very simple operation right now. But somehow it's important to observe that, you know, you can somehow think of these operations by really, you know, exploiting this, this philosophical connection between pseudo distributions and actual distributions. Okay. So now let's imagine the following. Suppose you had a certain, suppose mu was an actual distribution. Okay. Suppose, so this is like a thought, some kind of a thought bubble. So let me just like demarcate it by this rectangle. So suppose mu was an actual distribution, then here is what you could do, right? You know, you could design a new distribution which does the following: sample x from mu, and then, you know, output x or minus x uniformly. Okay. Now I claim that, and so this is like some kind of a symmetrization operation, right? So what's happening, let's now understand, you know, what happens to the first and second moments of the distribution mu when I do this operation. So if I output x and minus x uniformly, then clearly the mean of the distribution, mean of the new distribution is going to be 0, right? So this operation, one thing it has done has, one thing that it does is like it makes the mean 0. And what happens to the second moments? What happens to, what happens to this guy, expectation of XX transposed? I claim that nothing is changed there, right? Because XX transposed and minus x transposed is exactly the same. So this operation of just, outputting x or minus x uniformly by first choosing a sample x from mu preserves the second moments and makes the mean 0, okay? Now, of course, we cannot do all this sampling, etc. for pseudo distributions, okay? But one thing we can definitely do is, look at this pseudo distribution. Look at the pseudo distribution. With mean 0 and covariance, or actually second moments, equal to the second moments of XX transposed, okay? So I guess I'm claiming that even though our initial pseudo distribution was not mean 0, I can kind of, without loss of generality, assume that. Now, why, like one thing I should be, so the new thing is clearly a pseudo distribution because this is still PSD. This matrix is still going to be positive semi-definite. But one thing I need to be concerned about is how I modified the value of the FG polynomial. So what's happening to, I guess in this thought process, we could have also wondered what's happening to expectation of this FG polynomial. And I claim that, the expectation of the FG polynomial is also going to be invariant. Why is that? So remember that FG of x equals sum over all edges, 1/4 factor, xi minus xj square. And, you can expand it out as xi square plus xj square minus 2 times xi xj. And now the point is that over the hypercube, xi square and xj square are exactly equal to 1. And so this is simply 2 minus 2 times xi xj. Okay? And in particular, the expectation of this polynomial depends only on the second moments of the pseudo distribution. And so because it had no dependence on the first moment, even if I make the mean 0, nothing really changes. Okay? So I guess this was just to convince you that without loss of generality, can assume that E tilde mu x is 0. Okay? Very good. Now what? So next, now, so our goal is the same. We have to transform mu into an actual distribution. But I guess what I've told you is that we can assume that the mean of mu is 0. And so now, we take Gaussian. So take Gaussian random variable with mean 0 and covariance XX transposed, right? And in order to make this into a distribution over the hypercube, I'm simply going to take sine of this. So, set xi, let's call it maybe hat, equal to sine of gi. So gi itself could take real values. I'm just simply, replace it by its sign. This way, it's going to be a value in plus or minus 1. So definitely, this x hat vector lives in plus minus 1 to the n. And this whole process induces a distribution over the hypercube, namely the distribution which can be sampled as first taking a Gaussian with the second moments E mu XX transposed, and then, just taking the sign of it. In particular, this is an algorithmic process. It's in fact an efficient algorithm to take a distribution with given second moments, and assuming that you can sample from a Gaussian with that second moment, with that covariance, you can actually, convert it into a distribution over the hypercube in this two-step way. Okay, so this is going to be our transformation. So we're going to, call mu prime the distribution of x hat. Okay, and we're going to prove that this particular choice of mu prime is going to satisfy the property we wanted. In particular, this particular mu prime is going to satisfy. So, we'll show, so claim E mu prime FGX is at least 0.878 of E tilde mu FGX. Okay, let's prove this. And actually, there is in fact only, so let's, call it maybe subclaim. There's only like one simple calculation that will actually yield this result to us. And this particular calculation, for a different reason, actually was already done by Shepard. So let's call it Shepard's lemma. And it says the following. So let's put it, oh no, what did I do? Okay. So let's write it down here so that I have some space up there. So let's understand, what do we have to prove? What do we have to do to, analyze this claim? So let's understand, so let's try to understand what happened to a particular edge. Okay. Because, by linearity of expectation, fg of x breaks into like some of these, xi minus xj squares where ij is an edge. So I can try to look at what's happening to a single edge separately. Now, on the right hand side, I get something like e tilde mu of xi minus xj square, right? And on the left hand side, I get e mu prime of xi minus xj square, right? And of course, all of them are scaled by a factor of 1/4. But remember, x hat is a distribution over the hypercube. So on the right hand side, if you look at this x hat I minus x hat j squared, then it either takes the value 4 or 0, right? And so this number is simply equal to the probability that x hat I not equal to x hat j scaled by 1/4, right? Because whenever it's not equal, it's going to give me 4. And so that's exactly what's going on, right? And so in this claim 2, we are going to really compute this, okay? So remember, x hat was the sign of the Gaussian vector g. So Shepard's lemma is going to say that the probability that sign of Gaussian gi is unequal to the sign of Gaussian gj. Let's maybe write it on the right hand side instead of a ratio, is bigger than equal to arc cos rho over pi times expectation of gi minus gj squared. Yeah, I guess that's fair. So let's understand what I have here. They're saying, oh, and let's maybe also write down what rho is. For rho equal to tilde e of xi xj. Okay. So this Shepard's lemma is trying to, understand the probability that once you take sign of the Gaussian, the sign of two correlated Gaussians are unequal. So remember, x hat I and x hat j are signs of gi and gj. So on the left-hand side, you have the probability that are unequal. And, by what we just discussed, they allow you to compute the left-hand side of this inequality in claim 1. On the right-hand side, you have a certain ratio thingy appearing. Let's ignore that for a second. And then it multiplies basically the same thing that appears on the right-hand side here. Okay, right-hand side of claim 1. So on the right-hand side, the edge ij, the contribution to the expectation is going to be e of gi minus gj squared. Remember, I can write it with Gaussians because the second moments and the first moments of the Gaussians are the same as that of, the pseudo distribution mu. And so, on the right-hand side, I have something that appears on the right-hand side of claim 1. On the left-hand side, I have what, I'm interested in understanding. This probability that x hat I is unequal to x hat j. And I'm saying that they are basically, within this factor arc cos rho over pi, 2 times arc cos rho over pi of each other, okay? Where rho is, the correlation between xi and xj, which remember is same as correlation between the Gaussians gi and gj, okay? So I claim that, if you have this, you're in fact done. Why are you done? So I want to say that this, I'll prove this claim to you in a second, but I want to claim that claim 2 implies theorem 2. And, you know, it just requires computing the minimum of this, you know, right-hand side over all possible values of rho. So the claim 2 implies theorem 2 by observing that minimum over all rho in plus minus 1 of 2 arc cosine of rho is at least 0.878. In fact, you know, it's some irrational number, so it doesn't stop here. This is just, you know, the first 3 digits of its decimal expansion. But basically, you know, it's some number. Let's, in fact, you know, give it a name because it's some irrational constant. Let's call it alpha GW. So, you know, all this is proving is that, you know, the ratio of these two numbers is at least alpha GW. And so now, you know, what you've learned is, you know, that, so this implies that E mu prime of any edge x hat I minus x hat j square is at least 0.878. Actually, let's keep calling it alpha GW of tilde E mu of xi minus xj square. And so now, you know, you can just apply linearity of expectation and be done. So, you know, I can just sum it up over all possible edges to a quarter factor. And that, you know, proves a theorem. Okay, so that's very simple. You know, once we analyze, you know, each edge separately and prove, you know, this ratio, this one, you know, is simple. I'll give some intuition at the end, but, you know, this is basically, you know, some simple calculation. Just like minimize this, you know, over all rho. You can, in fact, determine, if I remember correctly, it's like minimized at rho equals minus 0.69. So in a second, I'll explain to you where that comes from. Yeah, that's that the ratio is minimized and the minimum value is 0.878. So we are going to be done. So let's, you know, go ahead and prove this claim 2, which is basically the non-trivial part, which is also going to be really simple. So, and, you know, in some sense, you know, so far, so we used in some sense one property of Gaussian distributions already, that the fact that, you know, for any PSD matrix and any vector, there is a Gaussian distribution that with that vector as the mean and, you know, the PSD matrix as the covariance. We're going to use, you know, the second property. In fact, you know, it's kind of obvious once you think about it, but, you know, I'm going to express it now. So if I have any two Gaussians, so let's say, you know, so we, in fact, you know, we are looking at these two Gaussians, GI and GJ. And these are correlated Gaussians, right? So in fact, we know that their correlations look like EGI-GJ equals E tilde mu xi xj, which, you know, if you remember, equals rho. And we also know that EGI square equals what? Just to, you know, make myself, you know, just to convince myself that you are all here and paying some attention. Can someone tell me what EGI square is going to be?
One.
All right, there are lots of ones in the chat, so I'm going to assume that we're all following. So, you know, we know that the expectation of the square of these Gaussians is 1, and the correlation between them is rho, okay? And so now the observation is that if I give you two scalar random variables whose distribution is jointly Gaussian, and I tell you their mean and, you know, correlation, then in fact, there is only one Gaussian distribution in the world which satisfies that. Okay, so, you know, a Gaussian distribution is completely specified by mean and covariance. It's a very simple basic fact, which we kind of been using for a while, but it's important because now I'm going to give you a different way to, you know, get a jointly Gaussian random, like jointly Gaussian two random variables, which have the same correlations. And this way of looking at them would actually help me analyze them, okay? So let's say V and W are two-dimensional vectors. Let V, W be two vectors in R2 such that length of V equals length of W equals 1. And let's say that inner product equals rho. Okay. Now take H to be a standard Gaussian random variable in 2 dimensions. So 2D standard Gaussian. By standard Gaussian, I mean Gaussian with mean 0 and, you know, correlation 0. And, all variance is 1. So, this is a Gaussian where, EHI square is each H1 square equals EH2 square equals 1 and EHI HJ is 0. And now, consider the following random variables. Let's call them maybe GI hat, H inner product V, and GJ hat equals H inner product W. Okay. And I guess the point I'm trying to make is that if you now compute EG hat I squared, then actually it equals EHV squared. And, V is a unit vector. So for a Gaussian H and unit vector V, this is actually going to equal to the norm of V. So this is actually equal to 1 by our choice of V. So this is similarly, the same calculation shows that also equals 1. And E G hat I, G hat J equals rho. Again, you can convince yourself by, just simple direct computation. So what I have done is, in some sense, given you a different way to sample two Gaussians with the same distributions as GI and GJ. So in particular, their correlation is the same and, the expectation of the square is the same. And now it's nice because I can do some geometry with it, right? I have two vectors V and W and I have basically the inner product rho. So this is going to help me reason about them, okay? So remember, what are we interested in? So we are interested in computing the probability that sine of GI doesn't equal sine of GJ, okay? Which is same as the probability that, that sine of G hat I is not equal to sine of G hat J, because G hat I and G hat J have the same joint distribution as GI and GJ. And so now let's try to understand this quantity because we're going to be able to, just do it with simple geometry. So there are 2D vectors of length 1. So I can draw them on a circle. Let's call this V and let's call this W. And, we said that VW is rho. So the inner product is rho, which means that the angle here. So remember, like if I have two vectors of length 1, then the inner product is simply, cosine of the angle between them. So I know that the cosine of the angle between them is rho, which means that this angle must be arc cosine of rho. Okay. So we have two vectors with arc cosine rho angle between them. And we're trying to understand what's the chance that if I take a random Gaussian H. So remember G hat I and G hat J, we exactly have an expression for them. So we are basically asking what's the chance that H inner product V has a different sign from that of H inner product W. Right? We just like using this procedure that we described to sample, G hat I and G hat J. So now we're asking what's the chance that a standard random Gaussian, and you take the standard, we take the standard Gaussian H and take inner product with V and W. We are trying to understand the probability that these two get different signs, right? So now we're going to use another property that we, proved on the homework, namely the rotation invariance of a Gaussian, okay? So in particular, so, I can draw this H as, so H is also a two-dimensional vector. H is a Gaussian in 2 dimensions. So it looks like this, right? Let's say this. And now, the main observation is that, the distribution of H is rotation invariant, okay? Which means that, if I take H and scale it down to a unit vector, then it's going to be uniform over this circle, right? We proved rotation invariance property on homework 0. So this is basically what holds for H when you normalize its, length to be 1. And so we are trying to understand that is rotation invariant distribution. What's the chance that, sine of HV differs from that of sine of HW? Now, this is, HV and HW are just projections of V and W on direction H. And they have differing signs only when, H, when normalized, lives in the region which I'm marking out here. Like basically the region between, the smaller arc between V and W. So let's maybe use yellow to describe it. So remember, this angle is still arc cosine rho. And so now we have reduced our problem to just computing what's the chance that a rotation invariant vector, lives between these two arcs that subtend an angle of arc cosine of rho each, right? Now, because of rotation invariance, H is equally likely to be anywhere on the circle. The sum of the angle total is 2 pi. So the chance is basically 2 arc cosine rho over 2 pi, which equals arc cosine rho over pi. Okay, let me again pause for 30 seconds and make sure that you understand this calculation. All we have proven is that if you have two Gaussians with correlation rho and their variances are 1, their mean is 0, then the chance that their signs are different is exactly equal to arc cosine rho over pi. So any questions? All good? Okay, very good. So now we are good to go. We can compute a calculation. We just have to notice. So now we were computing this ratio. So the other quantity in the ratio is simply E of xi minus xj square, which is same as E of gi minus gj squared, which just to belabor the point also equals g hat I minus g hat j square. And now if you expand out, this is equal to 2 minus 2 rho. And so what we have proven is that the ratio is arc cosine rho over pi divided by 2 minus 2 rho. So let me, instead of writing it again, ratio equals arc cosine rho over pi is 2 minus 2 rho, which equals arc cosine rho okay, I guess I messed up the 2 factor there. But that's it. It's like a very simple geometric calculation. You can simply compute this ratio and use calculus to minimize it over all possible values of the rho, which takes the value between plus and minus 1. Okay, so we are basically done here. Again, any questions? So it's a priori it might look like magical why this somehow is going to end up beating 0.5, but and I'll include this thingy on your homework, the coming homework. But you can use very simple series expansion to prove that you are definitely going to beat 0.5 with this. Okay, even if you don't want to do hairy calculus to prove what the exact minimum value of this expression is, you can quite easily convince yourself that the approximation ratio of this algorithm is going to be strictly bigger than 0.5. So this I'll phrase that as a problem. In fact let me phrase the result that you'll prove on the homework. So in fact, let's say corollary. Suppose max over x n plus minus 1 to the n of fgx, remember we called it opt g, equals some number 1 minus delta times the number of edges in G. Then the above rounding procedure actually sorry, let me write it in terms of the pseudo distribution instead. So suppose e tilde mu fg of x is at least 1 minus delta times e. So let's say that the SDP things, or the sum of squares of degree 2 things, that there is a cutoff size 1 minus delta times e, then e mu prime fg of x is at least 1 minus O of square root delta of e. Okay, so somehow if so in some sense you can think of this as something sensible when delta is very small. Of course, because there are constant factors here, this is not a sensible expression when delta is large. But what this is saying is that if delta is very, delta is small enough, then whenever you have a pseudo distribution saying that the cut value is 1 minus delta times E, then the rounding algorithm, this distribution mu prime that we produced, gives you a value which is like 1 minus O of square root delta of E. And you can use this to prove. So, this implies that, the approximation ratio of the algorithm is strictly bigger than 0.5. Okay. Good. So, again, are there any questions at this point?
So to actually find a cut which has the 0.78 ratio for approximation, you just sample from this distribution, or how do
Yeah,
you-
absolutely. Because the final distribution mu prime, we in fact gave a sampling algorithm to sample from it, right? We literally said, compute E mu of XX transpose, find a Gaussian distribution with the same second moment, and then, take the sign of a Gaussian, like a draw of the Gaussian from the distribution. So this particular thing was simply a sampling procedure from this distribution. So we in fact describe mu prime by giving a sampling procedure from it. So yes, in particular, we can sample a cut which in expectation cuts 0.878 fraction of the optimal number of edges. Does that answer your question?
Yes, that answered my question.
Okay, very good. So, okay, good. So, we designed a very simple, or actually, in retrospect, it was a very simple analysis. But, as we talked earlier, it took a while for people to come to this point. But, we designed a simple algorithm that achieves 0.878 factor approximation. And so it's very natural to ask, can we do better? And, Alex was asking this question earlier. We can also, think of it as in terms of, how can we improve this certificate? We use degree 2 SOS to give some certificate of upper bound on, FG of X. Can we somehow improve it, right? So the most logical question based on what we did today is, can we improve it with degree 2 SOS? Okay, can we somehow get a better approximation algorithm than, than just degree 2 SOS? And the answer to this is no. And in the last 15 minutes or so, I'll sketch a reason for it. Okay. And this is actually not that hard to prove. In fact, I'll give you a very explicit graph for which, in some sense, we can ascertain that, you cannot improve this. But that's just degree 2 SOS. Why should we stop there, right? In particular, we can ask the same question for degree 4 SOS and degree 6 SOS and degree 10 SOS. And actually, maybe you're not just looking for polynomial time algorithms. You can even ask it for degree log n SOS. Because, for whatever reason, you might be okay with even designing an n to the log n time algorithm, right? And even though for degree 2, we completely understand this question is open. So for all we know, at the end of this seminar, one of you could design an algorithm, using, let's say, degree log n SOS that improves on 0.878 factor approximation. Good. So that's in terms of SOS, but how likely is this, right? Like, how likely is that at the end of the seminar, one of you would actually have found such a better algorithm? So there is some evidence that, in fact, this may not be possible. And that is based on what is called as the unique games conjecture. So some of you might have heard about it. We'll actually discuss this in slightly more detail, I think, in 2 lectures from now. In particular, we'll describe what is the unique games problem. So in particular, this unique game conjecture is, is some conjecture about some, particular kind of problem being hard to solve. Okay, in particular, NP hard to solve. And I don't want to describe it right now in this lecture, but basically, it implies, so there is this famous theorem of Coate, Kindler, Mossel, and O'Donnell from 2004. And they proved that this conjecture implies that alpha GW plus epsilon approximation of max cut is NP hard for all epsilon bigger than 0. And so in a very precise sense, it turns out, and so remember this alpha GW, by the way, is the same precise, weird, irrational number that pops out when you analyze this two-dimensional geometry problem. Okay, so like the Shepard's lemma that we proved, alpha GW is basically the minimizer of this arc cosine rho over 1 minus rho kind of expression that popped up there. And so what this result is saying that take that particular weird irrational number, and if you ask the question of trying to approximate max cut, which is a tiny bit better than that particular irrational number, then any possible improvement on it is in fact going to be NP hard. Okay, so that's what is known under unique games conjecture. So you can now ask, is UGC true? Because, well, clearly that's what somehow governs whether we can improve this algorithm during the course of our seminar. So of course it's a conjecture, so we don't know. But just last year there was a big improvement in our knowledge of it. So Dinur, Cote, Minzer, and Safra, they proved the so-called 2-to-2 games conjecture. Again, I'll describe this problem to you in the lecture when we study unique games conjecture. But they proved the 2-to-2 games conjecture, which is kind of a close variant of UGC, but not quite UGC. They actually proved, that this variant of unique games problem is hard. So, let's, just simply call it a variant, a close variant of UG is NP hard. Okay, so that's our knowledge of of max cut, and as you can see, there's basically a number of very basic open problems. In particular, just analyzing degree 4 sum of squares relaxation of this for this particular problem, we don't understand how to do it so far. But going back, we can ask a more fine-grained question than the one we studied. So right now what we did is we said for all possible values of rho, we get this expression arc cosine rho over 1 minus rho whatever. And so let me maybe say it this way, right? Like so let's say, so suppose we have suppose opt of G is at least 1 minus delta times E. Okay. Then I said, that we can round to mu prime such that, the rounding value E mu prime FGX is at least 1 minus O of square root delta of E, right? So instead of asking whether we can, improve the ratio, we can somehow parameterize by the actual value. Let's say that the optimal happens to be 1 minus delta. What's the best thing we can do when the true optimal is 1 minus delta? It's a legitimate question to ask, right? And so, what we discussed today, I kind of, claim to you, and you will prove it on the homework, that the same algorithm that we saw today, the same rounding algorithm in particular, gives you something like 1 minus O of root delta times E size cut, right? So 2 things you can ask. Is this rounding algorithm the best algorithm? So we know that, if you try to minimize, like try to somehow, get the best possible ratio between the true value, the optimal value, and, the rounded value, and, you take the minimum over all possible delta, then that number happens to be 0.878 and is actually achieved by the rounding that we just got, right? But if I fix a delta and I ask the same question, it turns out that the rounding that we did today, that's, some people call it Gaussian rounding, turns out it's not optimal. So there's a generalization of the Gaussian rounding. It's called, in fact, it's a scheme of roundings called as RPR square roundings. which, they're kind of close variants of Gaussian roundings, but they're not exactly what we discussed today. Turns out that, in some regimes of delta, there is a way to do better than Gaussian rounding using this so-called RPR square roundings. And in the next lecture, we'll see an example of how that is done. Good. I guess that's all the information part I had. So now, in the remaining 25 or so minutes, I want to tell you about, why at least you can't hope to improve on this algorithm that we just saw with degree 2 sum of squares. Any questions till then? Good. So, so let's understand, what does it like? Okay, so we want to somehow show that, you can't quite do better than the theorem that we just proved with just degree 2 SOS. When we try to somehow solve the problem of max cut over all possible graphs, so trying to find, certificates of, max cut upper bounds over all possible graphs. So we want to somehow show, so, let's try the same, suppose you want a degree 2 SOS certificate of non-negativity for the polynomial opt of G over some constant C minus FG of X. Okay. So we proved today that for C equals 0.878, there is such a certificate, right? So we can ask, what's the largest C for which such a certificate exists? Like in particular, is there a certificate for 0.878 plus epsilon, right? It's a natural question to ask. So we will prove that, or at least, I'll prove something and I'll claim something else, that C equals 0.878 is optimal. And in fact, I'll do that by giving you a very specific graph, for which this fails. Okay, so my first graph, so, I'll give you a very specific graph. In fact, this graph is just the n cycle. Okay, so this is what this graph is. So it has, n vertices. And, let's say that the vertices number 1, 2, 3, so on. And there is an edge between 1 and 2, and 2 and 3, and 3 and 4, and so on, and then also n and 1. So okay, it's a cycle. Okay. So we're going to show that for odd n, this in fact serves as what is called as, a gap example. So I'll tell you in a second what this means. So, but we'll use this very specific graph to show that there cannot be better certificates. Okay. So how will we show this? So we will show, so let's write down a theorem and then, I'll interpret it for you. So let Cn be, a cycle on n vertices, n odd. Then can someone tell me what's the max cut what's the value of the max cut in an n cycle when n is odd? Feel free to unmute yourself. Or I guess write on chat. Good. There are lots of answers on the chat apparently. So it's n-1, and so so the important thing to notice is that because it's an odd cycle, you cannot cut all edges. Okay. So there is no way. So in some sense, whichever way to divide the two vertices, whichever way you try to divide this n vertices into two parts, you will have to include one of the edges on one part at least. Okay. So and so don't want to belabor this point, but like one way to think about it is, what will you do? If you, so let's say you try to start building a partition on one side, you try to take 1 on one side, then you don't want to take 2 because you want to cut this edge. So let's say you'll take 3, and then you'll take 5, and so on. But the point is that now, because n is odd, you'll end up, picking n on your side. In which case, the edge 1, n would be included on your same side, which means that the cut will only contain n minus 1 edges. Okay, and this is basically the max cut in it, so you can't cut all the edges. So I'm going to write this as 1 minus 1 over n times the set of all edges of the graph. Very good. Despite this, there is a pseudo distribution of degree 2, let's say mu, such that tilde e mu of fcn of x is at least 1 minus O of 1 over n square. So notice that 1 over n square is tinier than 1 over n, and in fact it gets tinier and tinier as n increases. So this is this value here is much larger than the true max cut. Okay, so in particular, if you choose n as 1 over delta, then opt of Cn is 1 minus delta, while this theorem is claiming that opt SOS2 of Cn is at least 1 minus delta square. Okay, up to constant. So let's like this. And so, remember this claim that we made earlier? Let's maybe quickly go back and look at it. So this claim where, we took the pseudo distribution of value 1 minus delta and rounded it to a value 1 minus O of square root delta. Well, this particular claim shows that you cannot actually improve on it, at least, up to the constants in this O factor here. Like in particular, you can't hope to round to, you can't hope to round a pseudo distribution of value 1 minus delta times E to something which is, sorry, keep missing this factor. So something which is, better than 1 minus O of delta square times E, because there simply may not be such a cut. Okay, does it make sense? Again, feel free to ask questions, but basically this theorem says that at least this small delta version of the corollary that we stated. So this implies that the corollary for small delta is tight up to constant factors. Okay, but you may be wondering, okay, but that's just a fixed constant factor. That's just only up to constant factors and only makes sense for small delta. What about this 0.878 or whatever alpha GW that we were talking about? Can we improve on that? So it turns out that you can somehow blow up or just kind of take a natural upgrade of this example and prove that that precise 0.878 approximation factor that we obtained is in fact the best possible. And so in some sense, the way to think about it is that this cycle is a discretization of a two-dimensional sphere. So it's like a two-dimensional sphere, by the way, is just a circle. So the cycle, in some sense, should be thought of as a discretization of a two-dimensional sphere. It turns out that if you take discretization of a high-dimensional sphere, then in fact, you can basically get something which is tight for all delta and doesn't even lose constant factors. So this requires some effort. It's not exactly a 5-minute thing to prove, but also not very hard. Maybe it takes like 1 lecture to prove, which I will not do. Instead, I'll give you the reference. So this was proven by Feige and Schechtman in 2002. Basically use this discretized high dimensional sphere to somehow, prove that this alpha GW approximation thingy that we obtained is actually tight. Good. So now, I want to, give you some sense of how we prove this, for cycle. So let's, prove sketch of theorem. Oh no. It's going to be a sketch because I don't think I have enough time to do the whole proof, but this one is simple enough that I think you can fill in the blanks. So what's the idea? So the idea is to observe that if you look at this polynomial fgx, okay, and so right now, we are not even specialized to this cycle graph. Let's just look at fgx, in general. So remember, this polynomial was 1/4 times ij in edges xi minus xj square. So it turns out that this polynomial itself is in fact the quadratic form of a certain natural matrix associated with the graph G. Okay, so I want to describe, many of you probably have seen this matrix before, but I want to describe this to you. So it's called the Laplacian matrix of the graph G. So all of you are probably aware of the adjacency matrix. So, A is basically the 0, 1 indicator of the edges of the graph. Laplacian is just like a shift of this matrix. So let's say that, for our purposes, we are dealing with only the cycle. So let's say, our graph is regular. So let's say, degree of every vertex is some number d. Then Laplacian is simply degree times identity minus the matrix A. Okay. So, what I did was, just took the adjacency matrix and shifted it by this degree times identity. Okay. Why am I doing this? What's going on here? So, so the nice fact is that this shifting makes this matrix always positive semi-definite. Okay, so it's not very hard to prove that this matrix is always positive semi-definite. Okay, and I'll actually prove that to you in a second, because I guess I'm going to prove to you that all quadratic forms. So, let's maybe write it down more carefully. So let's call this matrix LG, then claim X transpose LGX actually equals sum over the edges of xi minus xj square, where E is basically the edge set of the graph G. And, in particular, this is always non-negative because it's a quadratic form. And on homework 0, you prove that if all quadratic forms of a matrix are non-negative, then that matrix, in fact, is positive semi-definite. And so, this implies that this matrix LG is always PSD. Okay. So let's work modulo this claim for now, because I want to give you some more ideas before I go back and verify this. So now, so our goal, so basically the max cut goal is same. Max cut is same as, maximizing over all possible Boolean valued vectors, X transpose LGX. So far, so good. So for a second, let's understand the related question. Maximize over all possible vectors. And let's say, let's just fix the L2 norm of the vector to be square root of n. So like, I'm just like fixing the L2 norm to be the same as that of a vector, which, is in plus minus 1 to the n. But I'm dropping the constraint that each coordinate be plus or minus 1. Then, I can look at the similar maximization problem. Wait. I can look at the similar maximization problem with just this constraint thrown in. Okay. Can someone tell me what this maximization problem is, or what its value is? This is like a very nice quantity of LG. Okay, so there is an answer in the chat, and I hopefully everybody agrees that this actually equals square root of n, actually not square root of n, times the spectral norm, of the matrix LG. Okay, so this is the maximum of all possible quadratic forms on vectors of length root n. And again, on homework 0, I think you proved that this actually equals, the norm, the square of the norm of the vector times the spectral norm of the matrix L sub G. Okay, and so actually, this is a very easy to compute quantity. And again, on the homework, we kind of gave you some algorithm for computing it. I guess we claimed that there's an algorithm to compute it because this is equal to the largest singular value of LG. And you can compute, or at least approximately compute singular values of LG by just taking its SVD. We just have a polynomial time algorithm. We kind of claimed it in the homework 0, so we're going to assume it. So this related problem, I guess what I'm saying is easy, right? And so all that MaxCut is doing is placing this Booleanity constraint on top of this what can be thought of as a spectral norm or eigenvalue maximization problem, right? So this actually just equals the maximum eigenvalue of L sub G. And we are just trying to understand, if I add the extra constraint that the vector be Boolean, what happens? How can I solve that problem? And actually, we already know that that makes the problem very hard. If I place the Booleanity constraint, we know that it makes this MaxCut problem very hard. I'm sorry about the weird light, by the way. Always happens at around this time. I have to find a new position to sit in. But okay, hopefully it's not too distracting. So this is an eigenvalue maximization problem. This was easy. We have this Booleanity constraint, and we already know that makes the problem hard, and we found some approximation algorithm. Good. So now what? So how do we construct? So now with this prologue, I can tell you how do we construct a pseudo distribution for the cycle that that satisfies pseudo distribution mu of degree 2, that satisfies tilde mu fg of x is at least 1 minus O of 1 over n squared. How do we do this? Well, let's try to understand. If I wanted to construct an actual distribution, what would I do? Well, if I had to construct an actual distribution, I simply have to find vectors that take as, so we already saw that fg of x was equal to x transpose lgx, the quadratic form. So if I want to maximize this, I should choose vectors x that take as large a value of this quadratic form as possible, right? Clearly. And so in particular, I should try to choose vectors. So choose x, choose a distribution on x that are in the largest eigenspace of L sub G. Right? Intuitively, if I want to somehow, construct a distribution where fgx takes large value, then I should make the distributions be supported only on, x's that live in as large an eigenspace of L sub G as possible. Okay? But of course, there may not be any Boolean vectors in it. So I cannot, there may not be any vectors with like plus or minus 1 coordinates. So in general, I won't be able to do this. But now, I want to somehow go back and look at the freedom I have in constructing only a pseudo distribution, not a distribution. So let's recall, what's a degree 2 pseudo distribution? Well, if I have to describe to you a degree 2 pseudo distribution, all I have to give you is this guy, right? And the only non-trivial constraint that Booleanity places on degree 2 pseudo distribution is that, so this is of course PSD, but that's going to be true for all all distributions in general too. The only non-trivial constraint that you get is that e to the mu of xi square must actually be 1, right? Because xi square over the hypercube is 1. This is a degree 2 constraint, and so this in fact must hold for all pseudo distributions. So in fact, you can prove that if mu, so let's maybe say it this way, mu is a degree 2 pseudo distribution over the hypercube, if and only if e twiddle 1x transpose is PSD, e twiddle mu is 1, and e twiddle xi square is 1 for all I. Okay. So again, I'll make this an exercise in your homework, but this is very simple to prove. I guess what we're observing is that the only non-trivial constraint that the pseudo distribution places by virtue of being on the hypercube is that the diagonals like this e to the mu of xi square must be exactly equal to 1. And so now, our goal is, so now, what do we want to do? Our goal is to, and so remember, for FGX, in fact, only, so let's maybe even make the claim. So in fact, for FGX, because it only depends on, expectations of xi and xj, like only depends on like this degree 2 expectations, we only need to, worry about e to the mu of xx transpose. So in some sense, the goal is to construct this guy. So this is a matrix which looks like, has ones on the diagonal. It's an n by n matrix, ones on the diagonal. We don't know what we should place on the off diagonal, but our hope is that, if this is some matrix M, then our hope is that, if I take FGX, then this is, 1 minus O of 1 square. Okay. So how are we going to do this? So the idea, so now I can describe to you. So we already said that there is no single vector with Boolean coordinates, in the largest eigenspace of L sub G. That makes, so, there is, so, okay, let me be more careful. So the first observation is that, L sub G's top eigenvalue, the largest eigenvalue of L sub G, in fact, does equal 1 minus O of n 1 square. So, if I could find a Boolean vector, like a vector with plus or minus 1 coordinates in the eigenspace corresponding to this eigenvalue of L sub G, I'll be done. But there is no such vector, okay? In particular, because we know that the max cut is 1 minus, 1 over n. So what do we do? So we can prove that, in fact, this top eigenspace is 2-dimensional. So there are like 2 vectors in it, okay? And so what we're going to do is this weird magical thingy. We're going to do, we're going to set M, this matrix. So let's call these vectors, I don't know, V1 and V2. So we're going to set this matrix to be V1, V1 transpose plus V2, V2 transposed. Okay. And it turns out that the structure of the eigenvectors is, because of the virtue of the, the structure of the eigenvectors, it turns out that even though the individual diagonal entries of V1, V1 transpose are not 1, because V1 and V2 are not Boolean, the sum of their diagonal entries is actually 1. So in fact, this matrix does look like 1, 1, 1, 1, 1, and something, something here. And the point is that both these vectors are in the top eigenspace of L sub G. So they do take large values. They do take values 1 minus O of 1 over n square. Okay, so let me maybe summarize this idea this way.
Professor?
Yeah.
Are you sure the sum is 1 and not a constant?
Well, we can always scale, right? I didn't say that V1 are unit vectors.
Yeah, okay, sure.
And so, basically what was our idea? Our idea was that there is no Boolean coordinate eigenvector of the top eigenspace of L sub G. But but somehow, there are 2 vectors in it. In fact, it's a 2-dimensional eigenspace. So these are in some sense, the spanning set, such that, the sum of their outer products has diagonal 1. Okay. So I have only 3 minutes. So, let me claim the structure of the eigenvectors and, leave verifying this to yet another exercise on the homework. So turns out the cycles eigenvalues are kind of very nice. We completely understand them. So the eigenvectors of cycle look like this. So, remember that I have labeled the vertices of the cycle as, integers 1 through n. And so, I'm going to describe 2 kinds of vectors, xk and yk. And I have to give you their values at all possible integers, because that's how I'm going to think of the vertices of, the cycle as. So xk of u is going to look like cosine of 2 pi k u over n. Yk of u is going to look like sine of 2 pi k u over n. And k ranges, so k ranges from 0 up till n over 2. I'm saying strictly less than n over 2 because remember n is odd. Okay, so in fact, let's write it down like this because it's even better. So k takes the value at most n minus 1 over 2. Okay, and actually now, you know, at least if you believe this form, it's easy to verify why xk transposed plus yk transposed has diagonals 1. Well, because the diagonal entries of this matrix is going to be, you know, square of the sine of some, you know, it's going to look like, you know, sine square theta plus cosine square theta, where theta equals 2 pi k u over n for every coordinate u. And, you know, that's going to be equal to 1 because of basic trigonometry. Good, but I don't have time to, you know, verify the eigenvectors of C sub n for you and also do this construction in detail, but I'll add it as a guided exercise in the homework. Good, so, you know, that finishes our lecture. And as usual, I'll stick around for like 15 minutes or so to see if there are any questions. Oh, the sun is kind of, okay.
Hey, Pravesh.
Yeah.
Yeah, so there's actually a discussion in the chat, and
Okay.
yeah, so I would love to like know more about this. Basically, Jeff is saying that all the graphs that we know are sort of easy. We don't know any hard graphs that.
It depends what we, okay, so here's the question, if I understand correctly. You're saying, you know, what's a graph for which, let's say, degree 4 SOS does not, you know, give a better than 0.878 approximation? Is that a correct understanding of the question?
I guess. Let me look at what they're typing.
Okay, it's a long message. Let's see.
I guess the original question, I'm
Okay.
not sure if this is what it was talking about, was that like suppose, so my understanding, maybe I'm missing something, but my understanding is that the way this whole SOS algorithms at the end of the day is going to work is that we try to verify whether there exists a pseudo distribution. The pseudo distribution is used to know that the value of the objective function is larger than something, and then so we can increase the objective function by 1 and try for that. And this,
Sure. Yes.
But and then of course for a given objective function, you run an SDP, and the SDP gives you the pseudo distribution.
Yes.
So the I guess the original message, I guess the issue is that like we're getting this approximation from the fact that if you consider like the arbitrary space of all possible pseudo distributions, if you try to approximate their covariance matrix by distribution over the hypercube, you're going to suffer this factor loss.
Yes.
Whereas if you want to just approximate by a Gaussian, you don't need to suffer anything. So in general, you have to, for arbitrary pseudo distribution, you have to just suffer this loss when moving to the hypercube. But I guess my question was, like, suppose that like you knew something about the structure of the pseudo distributions which should be returned to you as a function of the input instance. Like I promise you have a certain type of graph. I also promise you that all pseudo distributions that will be returned by this SDP. This is like an algorithmic promise as well as an existence promise. You can find a certain kind of structured pseudo distribution that has the property that's better approximated by some distribution over the hypercube than this worst case bound, which always holds for all pseudo distributions. Then this would there's like two hypotheticals here. First existence, second, it has to be algorithmic that you can find these structured pseudo distributions.
Yes.
This would presumably give you a better algorithm for this subclass of graphs. I was also wondering if this was related to the LP rounding algorithms, which came prior to the SOS work that you had mentioned earlier.
So actually, yeah. So there were LP rounding algorithms that work for special classes of the graph, but I don't think the idea was kind of related. Like somehow the idea was, use some structural assumptions on the graph, like it's planar or whatever. But your question is interesting because not only, we actually, in some sense, we don't even have to be, vague about what structure in the pseudo distribution makes the rounding, achieve this 0.878, tightly. We literally know that. So, if you take ij as, let's say a random edge of the graph, okay, then in some sense, we know that the weird, like the worst case pseudo distribution is one, where, on an average, this looks like rho, where rho is that, so let's call it rho GW, where rho GW is like, that precise minus 0.69 value. Okay. So we know exactly the kind of pseudo distributions that are bad for rounding. Okay. In fact, you can prove that literally the same rounding that we ran, if the pairwise correlations among the edges are like different from rho GW in either direction, then in fact the rounding gives us a strictly better than 0.878 approximation. Okay. So in fact, your question is very precise. In fact, can I somehow generate a pseudo distribution where the pairwise correlations on an average are, far from rho GW? That's all we are interested in, right?
Yeah, so I guess it's not known whether I guess it's not known whether certain classes of graphs allow you to verify the existence of such pseudo distributions.
I mean, there are instances of graphs, for which people have proven results, not via this route. But I guess I wanted to point out that it's a reasonable question. For example, so here's something what you can ask. If I take a degree 4 pseudo distribution, okay. So we started with a degree 2 one today, but can I take somehow degree 4 pseudo distribution? And I don't know, massage it a little bit to get some new degree 2 pseudo distribution, where on an average, the pairwise correlations are far from rho GW. This is a very legitimate strategy. Nobody knows how to make it work, but it's a very legitimate strategy in order to, get a better than 0.878 approximation from MaxCut. It's just that we don't know how to do it. And in some sense, you don't, as we discussed, we don't even have to start from degree 4. You could start from, degree log n pseudo distribution, because we don't even, have, so right now, we don't even know if, let me in fact pose it as an open question. Is there a 2 to the root n time algorithm to get 0.878 plus 0.00000001 approximation for MaxCut? We don't know if there is such an algorithm. So in particular, one thing you could try to do is like start from a root n degree pseudo distribution and do something to it to get a degree 2 pseudo distribution where the pairwise correlations on an average among the edges are far from rho GW in either direction, and then run Gaussian rounding, like the same thing that we did today. That's like a valid strategy to potentially, attack this question, but we don't know how to do it. Yeah, so I don't know, like I guess I don't have a more insightful answer than, I don't know, and I think nobody knows.
I see, but would this 2 to the square root n refute UGC?
It's a good question. So no, it won't. So this in fact is possible even if the UGC is true. So, we'll see in one lecture from now that in fact UG problem itself, the problem for which, the UGC states, hardness, has a 2 to the n to the delta time approximation algorithm. So in some sense, it's not, we definitely know that, even in like our wildest fantasies, it cannot be 2 to the n hard. It cannot be exponentially hard. It can only be sub-exponentially hard. And so, whatever problems you prove hardness by reducing from unique games, you can never derive, even in the strongest possible hardness assumptions, you can never conclude that, let's say like 2 to the root n time algorithm is ruled out in general. So yeah, in particular, we don't know, we have no reason, we have no, even under our strongest known hardness conjectures, we don't know if a 2 to the root n algorithm, which beats the algorithm we saw today for MaxCut, is ruled out or not. And for all we know, it's actually possible.